Today lecture topic is miscibility gap. What is miscibility gap? Miscibility gap is a region in a particular phase diagram which has a mixture of two or more phases in a particular region. So region of composition of mixture where the constituents are completely immiscible. That miscibility gap is actually a region in a phase diagram. What is phase diagram? Now, temperature versus composition diagram, and where the mixture of phases are there, and the mixture of phases in the individual phase are varying in composition, not in structure. You can tell that they are in the isostructure phases, but they are varying in the composition with respect to each other. But in order to understand this phenomena, certain key points one should remember. What we understood or learned from our previous lectures, that common tangents to a free energy curves always define composition region where phase separation may occur. So for this particular case of miscibility gap, and how phase separation occurring, what is the driving force? Phase separation lowers the overall free energy by splitting the homogeneous system into a weighted mixture of two separate phases. So that actually the important thing, like other transformation, lowering the free energy. So in the progress of this lecture, we'll understand how phase separation is driven by change in free energy, and also we will learn about the miscibility gap conditions and the correlation between free energy composition diagram and the phase diagram of that particular system. So now we go for first slide of this lecture. So to understand this, what we see, there is for example, you can take a system which is an isomorphous system, and you can draw the free energy curve, and what the free energy curve already draw in the slide. So of the temperature, how does free energy curve look like? If you draw it, you can see in the slide that there will be a particular temperature. If it is in the solid region of the phase, then the free energy of the solid, that can be alpha phase, will be lower with respect to free energy of the liquid phase. That is known. There will be a free energy curve of this liquid, which is, if you see in the picture, it will like something like that. And these free energy curves, if you can expressed in the picture in the terms of free energy expression we have given earlier, that it will be del G XB GB plus delta H mix plus RT XA, ln XA, and RBX, RXB into ln XB. That's expression. So if you want to see the miscibility gap here, how this free energy curve is going to change, that we have to understand. So the difference between this, that normal isomorphous system and the miscibility gap system, there is a positive interaction between A and B. Means the interaction parameter of solid is going to be positive here. So for they are not, A and B are not attract each other, they repel each other. So that deals to delta H mixing is positive, because delta H mixing is a tau of XA and XB of a regular solution. So all those things are known to us. So from this perspective, we are going to understand how things going to happen with respect to miscibility gap. If we try to draw and tell that del H mix versus composition, then and the left side of the your that slide you can see the picture del H mix versus the composition. So it looks like a curve, and it is in the positive side of the things because del H mix you are having positive because del S you are telling that is greater than 0. Now you are going to draw the temperature versus into del S mix point of view, and there you can write minus T del S, and that curve will be shown in the lower part of the left hand side figure, and it is already known to you. And you check that it is a symmetry function because it is actually xa ln xa plus xb ln xb, that part is there del H mix, and the magnitude of this difference between the things is based on the temperature. If the temperature is not too high, you will see certain kind of lower difference. Del H mix is lower than the del del S mixing is smaller than the minimum value of T delta S mixing. You would see that the delta G mixing, which is nothing but delta H mixing minus T into delta S mix. If this is a positive, which what we have seen here, but it is absolute value. So T is the absolute value. Now, if it is smaller than the negative value, then what will happen? The G of mixing is still negative. But so that del H mixing is still negative, then the free energy curve will be having a curve downwards. Now we have drawn, I have drawn that it will be like that. If you see there, the free energy curve will looks like what is presented in the left side of the slide. Now, if I try to concentrate on the free energy curve, the free energy curve would look something like a scenario where the T is much lower than the things. So it looks like a curve which having to hum. And is the extreme cases, if you go for, then slowly it will come to the bottom part and it will go up. So you concentrate on the left side of the figure. And I hope all of you understood that it's based on the value of temperature, the nature of the curve is changing, and that curve, that is a curve of G alpha. And to draw such kind of plot, I have taken one assumption, that is GA equals to GB equals to 0. So that's why that curves looks like a the both points are equal and it gives energy of A and gives energy of B, and they are connecting. So now we have to understand why this kind of bottom depression is there. If you assume that pure method terms are not there, then also you can, because that already we have taken that GA plus GB, AGF equals to GB equals to 0. Then you will get the expression of G alpha, that is tau XA XB plus RT in the bracket XA ln XB plus XB ln XB bracket complete. And if you do the derivative of that, already I have written in the slide, and we understood that if the XB and XA at value will be 1 in any cases, both cases you will get the minus infinity, and that actually that we can say, or let me say that slope of the free energy curve as a function of temperature of what it is omega value. However large positive or however large negative it is, these bound to be negative. That del G by del XB or del G by del XA bound to be negative. It is minus infinity. And because of that, the both side of the free energy diagram in terms of composition, you see that the free energy has to form because it forms the lower side, because the negative side, which is minus infinity towards this end. So you see, you will keep on increasing this positive value tau XA XB. If it is But it is going to, what if it is negative, then what is going to happen? That we understood from the isomorphous diagram. But you will see the curve will go down more and more if omega is negative. If you check on the isomorphous diagram also. But here case is not like that. It's go initially the negative in either pure side and then slowly, not slowly, is abruptly increasing based on the value of temperature. So free energy curve could be in the ultimate case, could even be like the curve what is written is a very big hump will be there, but he has to drop first to go to negative side, then it will increase. Both pure side of this. Even it can be very high value, but you have to get that. For the delta omega, if it is very high, the omega value will be very high positive. Then you can get such kind of extreme things. So then you see it drops by a small extent and that starts rising at the top. It's because you would see in all cases, it will never start from zero. It should be dropped and then rise. Why is it so? Again, I am repeating that del G, del XB, that diagram should be, so that derivative should be negative. Which you see here, and the moment you see a curve like this, I can say that this kind of scenario is happening due to del G by del XB. Now we have to understand the common tangent phenomena. Slope, if you see this curve, different point, there is a kind of common tangent you have to draw. So in order to get the equilibrium phase and particular compositions. Now, if you start drawing the composition common tangent, you will see like that, which is a tangent from both side ends, and the particular tangent where you see 2 points are there, and these 2 points are nothing but the equilibrium composition of the original space, which is now decomposing into two phase because of the limitation of the omega is very being positive. A and B are not able to dissolve into together, or so there are forces to segregation. So A dissolve into B, it's to some existence, but it likes more to be purer. So A likes B A atom, B likes B atoms, and that actually create a scenario that phase separation is occurring. And if you look at the point in the slide, if you look at the point in the slide, that is A and B point, I have marked that A point is A rich part and B point is B rich part. That way I put A and B. And if you see corresponding point in the gives free energy, gives energy and composition diagram, free energy and composition diagram, and corresponding point in the phase diagram in the middle of the slide, then you can understand that that is the point where the phase separation is going to happen. And if you go from the pure A line and the point A, then the alpha phase is stable. And if you go point B and pure B region, there is also alpha phase is stable. But in between that, from A to B, there is a two phases. One is alpha one is A rich phase, one is B rich phase. And if you are talking about A rich phase and B rich phase, both are having same structure, but their compositions are different. So that's why we are not going to name alpha and beta. We are going to name alpha 1 and alpha 2. So alpha actually transformed to the alpha 1 and alpha 2. So this part you have to understand very carefully, because this is the basis of understanding the miscibility gap phenomena. So this is alpha 1 and alpha 2, and you do not call them alpha or beta basically because both are same structure. It is actually one single phase which is decomposing into two with a structure remaining the same, expecting the composition are different. So as a result, the whole thing is alpha and alpha splitting into two, one having A rich composition, another having B rich composition, and that is how you see that it will have, we will have now more than about, we go to spinoidal kind of things. Forget about spinoidal, I will discuss later. If you look at what should be the free energy curve, this is a free energy curve. In the left side I have given, if that is the free energy curve which is leading to a simulation, a situation of alpha is having this decomposition and alpha 2 having another composition. So all are depending upon the temperature. If temperature, if you are increasing the temperature slowly, if you are increasing the temperature, what will happen? That hump will be lowered down. Those things, if we understand, we'll go to next slide. Here you see same thing, that there is a three temperature, T1, T2 and T3, and T1 is less than T2, T2 is less than T3, means highest temperature is T3. Now if you are want to see the corresponding, the left, complete left hand side is a free energy composition diagram. In between there is a phase diagram, and also right side composition diagram. Generally textbook or all the books you refer, you will get the picture and the left side to you or right side to me. You can say that where GA GB equals to 0 and that kind of straight line of parallel straight line. But it's not like that. It's very there is a different way you can represent the phase diagram, and in reality those kind of phase diagram is available mostly, that you cannot get the two equilibrium point in the same horizontal parallel axis to the x-axis. It may be ups and downs, so you can draw a common tangent, and also you can get the phase equilibrium phases. Now if you look at the common tangent in the left side of your slide, mostly that unequal or non-parallel to the horizontal axis, that free energy composition diagram, if you look at G versus X diagram, then what you will see that P and Q, the common tangent point of that curve. And if you go for left side of the P and try to draw a tangent, that is P dot point, at the P dot point, you will see all the free energy diagram in all composition are upper side of that particular P dot point, common tangent. Not common tangent, it's the tangent. Means there is no chances of phase separation. There is no chances of, because if you change the composition anywhere, the free energy will be higher than that tangent line. So there is no chances of segregation. But if you look at the point P double dot, it is right side of the P point, and if you draw a tangent and then you check that if you beyond the Q dot point, if you look at the figure, there is every chances are there to reach different composition for lowering the Gibbs free energy, because there is a lot of part of the free energy diagram, free energy versus composition diagram, there is a free energy curve are below the tangent drawn at P double dot points. So there is a lots of chances are there in order to lowering the free energy, they can go for different composition. So this is the point, there is a chances of phase separation. So if you look at this kind of scenario, then you can see that that alpha 1 plus alpha 2 phases can be seen. Now if you slowly increase the temperature from T1 to T2, then what will happen? The phase separation region will be reduced. And how it is reduced? If you look at other phase diagram, that is horizontal parallel diagram I just written in the right side of this slide, There you can see as T1 is going to T2 means temperature is increasing, the region of phase separation. If you draw the common tangent, you can understand the width of the region of the phase separation region or miscibility gap region is reduced. And if you go beyond a particular inflection point that you can tell the nodal binodal point or something, beyond that in T3 there will be a single phase diagram. There is no hump and nothing, so you don't have to go for common tangent. Single tangent will be sufficient to get the understanding of the chemical potential or phases stability and all those things. So in this way you can understand how free energy versus composition diagram is related to the phase diagram having miscibility gap region. In this slide, I have to talk about certain thing where you will see the correlation between thermodynamics and little bit of nucleation properties that is related to kinetics of miscibility gap. Here for thermodynamics you will get the driving force. Now again we have to find out certain things till now what we have discussed regarding that. What are the key points we learned so that we can go further. So we learned that common tangents to free energy curves define composition regions where phase separation, or you can tell two phase equilibria, occurs. And phase separation lowers the overall free energy by splitting the homogeneous system into weighted mix of two separate phases. And you can see which each have lower free energy than the starting homogeneous phases, that you can see from the previous slide discussion, that how P double dot tangent having a lower free energy composition existing in due to the that below the tangent there is a major good amount of significant portion of Gibbs free energy curve is existing. So composition of phases in two phase regions are given by tangent points, and the amount of each phase is determined by the Rivard rule. That is also important, and based on that you can find out individual phases what is the composition. Now another important thing from today's discussion, we understood that composition of two phase regions which are tangent points of the free energy diagram also become, you have to think that, also become phase boundaries on the phase diagram. So these are the concept we have understood with respect to miscibility gap. Now we are going to understand on the perspective of driving force, that is del H, del G. So the driving force, that is del G, what will be that at the L in that part, that L point, the common tangent, there is a strong chance, already I told that it has a strong chance for lowering the free energy, they can shift the composition. So B rich phase become more B rich and A rich phase will be more A rich. So there will be a two phase separation will be there with respect to composition, that is varying A rich phase and B rich phase. So now we have to again recollect the definition of phase. What is the definition of phase? Phase is chemically homogeneous, physically distinct, and mechanically separable. So why not, since the structure alpha 1 or alpha 2 having same structure, why you are not telling they are same phase? Because they are not obeying the first defining futuristic point of phase definition, that is called chemically homogeneous. Alpha 1 has different composition with respect to alpha 2 phase. That's why we are telling that alpha phase is transformed to alpha 2 alpha 1, although they are having same structure. Okay, so why these things is happening with thermodynamically? What is the driving force? If you want to understand, then if you look at the tangent construction at L point of a free energy curve, and you will see that Ln part, that is del G, that should reach to that point so that it will get the equilibrium point, and lowering from that you will not get any lower free energy. So always there is a demand thermodynamically that you have to go for lowering the free energy in order to get stable structure. So that is the driving force del G thermodynamically for the phase separation. Because if you see in the part where I have marked in arrow, if you go that direction, then only you can reach the equilibrium concentration, and those are the scenario where A rich phase and B rich phase will be produced. Now we are going to understand the kinetics part of that. Just we'll touch up that. Suppose in a phase there is an alpha phase, you lower the energy, then you are going to get alpha 2 phases, this alpha 2 phases, and which are having high in B concentration, means it is a B rich phase. Suppose we are taking that alpha 1 is A rich phase and alpha 2 is a B rich phase. But one can ask that overall concentration of the alpha phase are same. This is a homogeneous phase. So why there is no concentration gradient? And for such kind of phase transformation, you need little bit of diffusion, and diffusion is requires as per our common understanding that concentration gradient, or you can tell that change in mole fraction or something. But it's a homogeneous phase. There is no concentration gradient. Still, such thing is happening. How it is possible kinetically? In order to understand that, what you have to see that you have to understand the degrees of freedom of atoms. The atoms are having different degrees of freedom. That is rotational, translational, vibrational. So atom used to vibrate in this its mean position. So that fluctuation sometimes are due to different thermodynamic driving factor take a local clustering, and that local clustering can have different composition with respect to overall matrix, or you can tell the global composition. So such kind of local fluctuation may be very common, and in this case, since there is a more equal stable composition are available, so that's why that local clustering process are going to happen. And if you look at the plot, that alpha 2 alpha 1, that is the percentage of B, you can tell. So alpha 2 is a very B rich phase. Okay, now if alpha 2 want to be equilibrium with alpha, it is not going to possible, but overall composition should be same. That's why that is a weighted mixture of phases, weighted mixture of composition of different composition of phases. We have to tell that. So in order to get such kind, there should be another phase that is called alpha 1, and only alpha 1 and alpha 2 be in equilibrium, not alpha 2 can be equilibrium with the alpha. So that alpha 1 must be lower in concentration of B, and it should be A rich phase. So if you look at after certain times, that alpha 2 is growing in the last figure of the slide, and overall matrix transform to alpha 1. So now there is a two phases, that is alpha 1 and alpha 2. You can tell that in the alpha 1 matrix there is a alpha 2 precipitate out. So in this way, and in order to get that, there is a fluctuation is required in the atom, and atom is itself a vibration. Atom vibration is there. And then if you look at the small region I marked where B atom may decrease, because there is a chance of scenario where the alpha that they can that alpha 2 try to become B rich phase and grow, they will take the B atom from the alpha matrix. So slowly overall matrix alpha matrix transform to alpha 1 and alpha 2 phases are precipitated out. But one should remember that alpha 1 and alpha 2 both are having same structure, but their composition are different. That's why such kind of miscibility gap phenomena we used to see in lower temperature, and that is very important with respect to understanding the phase transformation, and it has strong dependence on thermodynamic as well as kinetics. So today lecture is over. Thank you.